Tonight's webinar is Perils of Cylinder Work with Mike Bush. Now, Mike probably needs no introduction, but I'll go ahead and give him one anyway. He is the owner of Savvy Aircraft Maintenance and Management. He's a CFI. He's a regular contributor to Sport Aviation. He's an A&P mechanic with his inspection authorization, and he was the Aviation Maintenance Technician of the Year in 2008. He's an EA member, and I know Mike also did a lot of forums at AirVenture Oshkosh 2015, as he will next year. So make sure that you make it next year if you missed him this year. Mike, are you with me?
I am, Charlie.
Welcome.
Thank you. Do you hear me okay?
I hear you 5 by 5.
Excellent. Okay. Good evening, everybody, and thanks for coming to the webinar. As Charlie mentioned, tonight's subject is the perils of cylinder work. And as any of you who have attended my previous webinars or read some of my writings in Sport Aviation know, I hate pulling jugs. And I hate pulling jugs because it's risky business. There are so many things that can go wrong when you remove and replace cylinders from a piston aircraft engine. And the risk goes up exponentially when you start removing multiple cylinders at the same time. And even more especially when you remove all of the cylinders at the same time, the so-called top overhaul. I say so-called because a top overhaul really isn't an overhaul from a regulatory standpoint, but it means that you're changing all of the cylinders, all 4, all 6 cylinders on engine at a time. Now, I said all 4 and all 6, so let me stop for a minute. We're going to be talking about flat engines tonight. I have a little experience with round engines. I have virtually no experience with Rotax or AeroV or other experimental engines. So if you wind up asking me questions about those during the Q&A, I will probably say that they're above my pay grade. So for the purposes of tonight's discussion, I'm going to be focusing on Lycomings and Continentals. A lot of what I say will apply to other flat engines, particularly VW variants and so on that pretty much go together the same way that Continentals and Lycomings do. But that's going to be my focus. In any case, and this is a subject of particular relevance to me because I just finished doing a top overhaul on the left engine of my Cessna 310. So I understand that sometimes we have to pull jugs. In fact, occasionally we have to do a top overhaul. And if you have to do it, there's a right way to do it that mitigates the risk, and we'll talk about that towards the end of the session today. But the reason I'm doing this is because it is my sense that most aircraft owners and the majority of A&P mechanics don't really appreciate just how risky cylinder changes can be. And so they don't have the appropriate level of caution or fear or whatever you'd like to call it, and they don't take all of the necessary steps to minimize the risk. And just to dramatize that, and this actually comes from an article that I ran recently in Sport Aviation. Let me just walk through a couple of very recent, hot off the press NTSB accident reports, just to illustrate the nature of the problem. The first one involves a Cessna 206 that crashed in Virginia, April 11th, 2014, and the probable cause report just came out about a month ago. One serious injury, one minor injury, obviously pretty totaled airplane. Let's take a look at what happened on this one. On the flight prior to the accident flight, the pilot slant mechanic, and I'm coincidentally both of these accidents that I'm about to tell you about involved airplanes being flown by the same guy that was working on them. I don't know why that was, but certainly as a pilot mechanic myself, I can tell you that that mechanics are very highly motivated not to make mistakes when they're working on airplanes they're flying themselves. But in any case, on the flight prior to the accident flight, the pilot mechanic noticed fluctuating oil pressure. So he decided to make a precautionary landing and do a change of the oil and cut open the engine oil filter, change the oil filter, which was an appropriate thing to do. When he cut open the oil filter, it was found to contain what was called in the NTSB report an excessive amount of metal. However, the pilot mechanic had replaced 4 cylinders out of the 6 about 4 months earlier. When he saw that metal in the filter 4 months later, he assumed that metal was normal as a result of the cylinder still breaking in. And I find that a little bit strange, because normally when we break in an engine after a multiple cylinder change or a top overhaul or even a major overhaul, we typically get rid of the break-in oil within about 10 hours. But in any case, he cut open the filter and he found some metal in there. He assumed that the metal was normal from the break-in and didn't and wasn't alarmed by it. Some personnel at the aircraft at the airport where he was doing this expressed concern about the metal, and they said, that looks like a lot of metal. I'm not sure I'd fly the airplane like that. But the pilot mechanic chose to complete the oil change and continue with the next flight, which turned out to be the accident flight. About 30 minutes after he took off, after this oil change, the engine made a strange sound, and then about 20 seconds later, it lost power. The ensuing forced landing was hard, as you could see from the picture that we started out with. The NTSB sent a team to investigate the accident. They pulled the engine, they had it disassembled, and the disassembly inspection revealed that the through bolts, and we'll be talking a lot about through bolts tonight, the through bolts, which are the big long bolts that hold the 2 halves of the engine together, were significantly under-torqued. And as a result of being under-torqued, the main bearings, 3 of the main bearings in fact, had shifted in their supports. And I'll be showing you pictures of all this stuff so you can visualize it if this isn't resonating with you. But they shifted. We colloquially say that they spun due to lack of through-bolt preload. And when a main bearing shifts and its oil supply hole becomes misaligned with the oil feed hole in the bearing support in the crankcase, then that bearing becomes lubrication starved, and catastrophic things tend to ensue very rapidly thereafter, as happened in this case. The NTSB probable cause report, probable cause on this accident read as follows. The probable cause was the pilot's decision to continue operation of the airplane with known mechanical issues, notably fluctuating oil pressure and metal in the oil filter, which was the result of under-torqued cylinder through bolts. Contributing to the accident was the mechanic's failure to properly torque the engine through bolts, which led to the eventual failure of the crankshaft. Let me parenthetically mention, before we go on to the next accident that I'm going to talk to you about, that cruise oil pressure should always be rock solid. If you are ever flying along in cruise and notice any sort of a fluctuation in oil pressure, you want to put that airplane on the ground right now and take it very seriously. Because there are only a very few things that can cause in-flight oil pressure fluctuations, and all of them are very bad. The 2 most common things that will cause oil pressure fluctuations are either a significantly large chunk of metal passing through the oil pressure relief valve, the thing that regulates oil pressure, which means that there are significant chunks of metal floating around inside the engine's oil system, or the displacement or shifting or spinning of a main bearing, which generally will lead to very quickly to crankshaft failure. So just as a word to the wise, anytime you're flying along, if you notice any fluctuation in oil pressure, you want to put that airplane on the ground immediately, and cut open the oil filter, look at the suction screen, figure out what's going on. Don't keep flying the airplane.
Hey, Mike.
Okay, and yes, sir.
You got a pop-up that's showing up on the screen about Windows 10.
Oh my goodness, I do.
Now that they've got their ad out of the way,
isn't that rude? Sorry about that. I appreciate that, Charlie. I heard you breathe there for a minute, and I said something's got to be wrong. Thank you for pointing that out.
We have some Mac users that don't like it.
Yeah, you'll edit all of this out of the video, right?
I don't know about that.
Okay. At any rate, moving right along. One more accident that I will talk to you about, and then we'll get into the nuts and bolts stuff here. And this involved a Beech A45, what's called a Mentor. It's I think it's a kind of a military. It's a military version of the Debonair, I believe. And this is an accident that occurred June 23rd, 2013, in Boulder City, Nevada, which is just slightly to the east of Las Vegas. It killed 2 people aboard, so it was a pretty serious accident, and you can see that the airplane was pretty badly messed up. The story on this one from the NTSB report: the pilot / mechanic, again, had replaced all 6 cylinders during the recent annual. He did a top overhaul, in other words. 3 days before the accident, the engine was operated and appeared to run fine. On the day of the accident, the airplane was returning to home base following a maintenance inspection of the wing. So apparently this was an annual that was being done sort of on the installment plan, and he had done this engine work at home and then flew the airplane somewhere else to have the wings inspected. It was probably actually an inspection of the wing spar center section, of which there's a repetitive AD on that particular airplane. As the pilot neared his destination, his home base, he noticed that an engine chip light had illuminated and declared an emergency with ATC. Shortly after the chip light came on, he noticed that one cylinder quit. The EGT went cold on that cylinder, and the engine started to vibrate pretty badly because it was running on 5 cylinders. The long story short, the aircraft wound up colliding with terrain in a nose-low attitude about a mile short of the airport, and the 2 people aboard died in the crash. Post-accident investigation of the engine, or examination of the engine, revealed that the number 6 cylinder had departed the premises. It had separated completely from the engine, and there was obvious fretting damage in the crankcase number 6 deck area, indicating that the cylinder had been moving around quite a bit. And the only way that can happen is if the cylinder hold-down fasteners did not have adequate preload. There are only 2 ways that can happen. One is that they weren't torqued properly to begin with. The other is that they were torqued properly, but somehow or other the preload was lost for some reason. Maybe presence of paint or sealant or something else on that surface. It should be a clean metal-to-metal interface. In this particular case, because the engine had almost no time on it since the cylinder work, the NTSB concluded that the overwhelmingly likely case was that the fasteners weren't torqued correctly to begin with and didn't have the necessary preload right from the get-go. The NTSB's probable cause on this one: the pilot mechanic's loss of control during an emergency descent following a loss of engine power while in cruise flight. Contributing to the accident was the pilot mechanic's incorrect assembly of the number 6 cylinder at the last cylinder change, which resulted in a separation of the cylinder and loss of engine power. And I could go on with more accidents like that. I won't. But this is something that happens on a regular basis. We see engines come apart catastrophically after cylinder work, particularly after the replacement of multiple cylinders simultaneously. So why is it so risky? Well, to understand that, you sort of need to understand how these engines are put together, and how a whole bunch of different things interact with one another. On our piston aircraft engines, unlike car engines, the cylinders are bolt-on assemblies. They bolt to the crankcase, typically with 8 fasteners at the base of each cylinder. You can see this is a mechanic putting a cylinder on, assembling it to the crankcase with a base O-ring, that red thing present, and there are, you can see 4 fasteners sticking out. There's 4 on the top, 4 on the bottom, 8 total. Yeah, I get another pop up here. I don't like that. That will ultimately hold that cylinder on. And here's a engine being put together, a 4-cylinder engine, and you can see the cylinders bolted on. And again, each cylinder has 8 fasteners, 4 on the top, 4 on the bottom, that hold those cylinders on. But the fasteners don't only hold the cylinders on. As it turns out, some of those fasteners are what are called through bolts that go all the way through the crankcase, and also hold the 2 crankcase halves together. This is kind of a very rough photo. I'm sorry for it, but it sort of illustrates how those through bolts go all the way through the crankcase and clamp the 2 sides of the crankcase together on either end of the main bearing supports. Here's a picture of a disassembled Continental 0200 showing the through bolt sticking out. Here's a picture of what I think is probably a Volkswagen engine, actually. That again shows how the through bolts go through. And here's a picture of a mechanic putting through bolts into a Lycoming engine that go all the way through from one side to the other. Now there are various configurations, but the most common one is that cylinders are typically, most commonly, held down by 8 fasteners, 6 of which are deck studs that simply thread into the crankcase and hold the cylinder down, and 2 of which are through bolts that go all the way through and do triple duty. The through bolts not only clamp the crankcase halves together right at the main bearing supports, but also serve as hold-down studs for a pair of opposing cylinders. So this through bolt is shared by 2 cylinders, 1 on each side of the engine, and also is responsible for clamping the engine together. Here are what the through bolts look like. The top one is a Lycoming through bolt. The bottom is a Continental through bolt. They're pretty similar. There are some differences. You can see that the Continental through bolts have a couple of O-ring grooves. In the middle, they use O-rings to seal oil at the engine parting seam. Lycoming through bolts don't have the O-rings, and they depend on a close tolerance fit and doweling to seal the oil. But basically, the Lycoming and Continental through bolts are very similar in design. And the main thing is that they go all the way through the engine and clamp the 2 halves of the crankcase together at the most important point, which is where the main bearings are located. Here's a set of Continental through bolts for a Continental 6-cylinder engine. There are 8 of them, 4 pairs that clamp the engine together. And here's a set of Lycoming through bolts. The crankshaft it runs in some bearing shells that look kind of like this, that mount in bearing supports or saddles molded into the crankcase halves. And you can see how the through bolts are positioned so that they clamp the two halves of the crankcase together, right at where the main bearing supports are. Now that's important because the thing that holds the bearings in place is what's called crush. The bearings are actually a little bit bigger than the bearing supports. And so when the crankcase is torqued together with the bearing shells in place, there's a force fit, or what's called an interference fit, that firmly hold those bearings in place in the crankshaft and the crankcase bearing supports so that they can't move. And that crush is absolutely crucial. If there's a loss of a bearing crush, then the bearings can rotate or shift in those bearing saddles. And just backing up one slide for a second, those three red arrows show the oil supply holes for the main bearings. And there's an oil supply hole that is machined into the crankcase, and there's a corresponding hole in the main bearing. And those holes have to be in alignment. If the bearing shifts in its saddle so that its oil supply hole doesn't line up with the oil supply hole that's machined into the crankcase, then the bearing becomes starved for oil, and really bad things happen. When these fasteners are tightened down, both the through bolts and the hold down studs, the tightening process creates what's called preload. And the concept of preload is extremely important. And this graphic tries to illustrate that. If we in this graphic, a spring scale, kind of like a fish scale, is being used as a proxy for a fastener. If we stretch the fastener to create a load on it, in this case of 1,000 pounds, then we put a block in there to hold it in place, then we can put pressure on that scale up to 1,000 pounds and nothing will move, so that the joint that thing is clamping together will be rock solid with loads up to that 1,000 pounds. If we put more than 1,000 pounds load on it, in other words, if we exceed the amount of preload on that joint, then things will start to move. And the same thing applies to these fasteners. When we tighten them, we put a strain on them, or what's called a preload. And that preload, it has to be greater than the largest stress that's going to be on that joint. And as long as the preload is greater than the maximum stress that is on that joint, the joint won't move. But if the preload is lost or is insufficient, then the joint will move. When the joint moves, we get wear. It's called fretting. You'll see that in a minute. And eventually the fastener will break, or something will shift, and really bad things will happen. And so the way we put the preload on those fasteners is to torque them. And basically, these are threaded fasteners, and we put a certain amount of torque on those fasteners, and a certain amount of torque is supposed to create the appropriate amount of preload in the fastener. Now, we could theoretically measure the amount of preload directly by using a micrometer and measuring how much that bolt or fastener stretches. But, and we do that sometimes. Lycoming rod bolts frequently are tightened to stretch, where they're micrometered, and they're tightened until they've stretched a certain number of 10,000ths of an inch. However, when tightening cylinder hold-down studs or tightening through bolts, it's just not practical to use that method. There isn't any place to put the micrometer. So we have to rely on the torque method, where we're applying a certain amount of torque to the fastener and assuming that that translates in a certain amount of tension or preload on the fastener. Now, the fly in that ointment and the problem with that method is friction, because when we torque a fastener, a great deal of that torque that we apply is not going into putting preload on the fastener, but it's going into overcoming friction. In fact, for a dry steel bolt, about 50% or so of the torque that we apply to the nut that attaches a steel bolt is spent overcoming the friction of the threads, and about 40% is spent overcoming the friction between the nut and the surface against which the nut is turning, leaving only about 10% of the torque that the torque that we apply that actually translates into stretching the fastener and creating preload. So the lion's share of the force we are putting on that torque wrench is going into overcoming friction, not going into putting tension on the fastener, which is really our ultimate goal. And those frictional losses are going to be even greater if the threads on those fasteners are not new, if they're damaged or worn, or the cadmium plating on the threads is worn. These fasteners that we're talking about on engines are all steel parts that are cad plated, and the cadmium plating is there for two reasons. One is that it inhibits corrosion of the fasteners, and the other is that the cad plating is very slippery, so it minimizes the amount of torque, of thread friction, and helps us get more of the torque wrench energy into actually stretching the fastener. So if the threads are worn or damaged, or the cad plating on the threads is worn, that's going to create even greater frictional losses when we tighten up the fastener, and that will translate into less preload on the fastener. Here's a crankcase that was in for an overhaul. And if you look at it closely, you can see that the threads are of those through bolts and of those studs are definitely worn. The cad plating is gone. They're not in terribly good shape, and it's very common during overhaul for those things to be reused. It is not only common, but it is universal. When cylinders are changed in the field, the studs are never changed. They're always reused. And the through bolts are almost never changed. They are reused. And so we're dealing with other than new threads that are typically not in wonderful condition. And this really makes it hard to get the proper preload. Here are some Lycoming through bolts that came out of an engine, and again, if you look at the threads, you'll see that they're not exactly in pristine condition, and that the cad plating is largely worn off. And so when we do a cylinder change and try to tighten up that fastener again, we're dealing with a very different situation than what the factory or the overhaul shop was dealing with when they assembled the engine initially. Now, to help overcome this problem of frictional losses when tightening these fasteners, one of the things we can do is to add lubricant to the fasteners to try to minimize the friction. And in fact, both Continental and Lycoming require that these fasteners be torqued wet. As you can see from this graph that shows the difference in preload for a given amount of torque for dry threads, that's the bottom line, threads lubricated with light oil, and threads lubricated with moly grease that's slipperier, if you will. You can see it makes a huge difference in the amount of preload that's on the bolt for a given amount of torque. And as I mentioned, both Continental and Lycoming both specify that cylinder hold-down studs and through bolts must be torqued wet. But we know from experience that mechanics tend to be reluctant to apply liberal amounts of lubricant to these fasteners because it's messy, and mechanics don't like to make a mess. And most mechanics don't realize the dramatic difference in what happens when you torque a fastener dry versus when you torque a fastener wet. There's also a vast difference in what kind of lubricant is used. And we see mechanics using all kinds of things to lubricate these threads. Depending on what lubricant you use, you may get a very different result. Another thing that interferes with the ability to get proper preload on these fasteners is simply the method with which the torque wrench is used. And again, this is the kind of thing, you know, I went through A&P training. Nobody ever mentioned any of this stuff to me. Mechanics are largely unaware that the way they actually swing that wrench makes a big difference in whether the fasteners are properly preloaded or not. The key is that if you use a click-style torque wrench, which the vast majority of mechanics use, it's extremely important to get to that click in one smooth motion rather than taking several different bites of the fastener, if you will. And that's a lot easier to do when an engine is being overhauled and is sitting on an engine stand. It's a lot harder to do when the engine is on the airplane and you are torquing these things down with exhaust components and engine mounts and all sorts of other stuff in the way. But if you don't get the wrench to the click point in one nice, smooth, fluid motion, you are very likely to under-torque the fastener because the static breakaway torque is significantly greater than the running torque, and so the wrench will click too early, and the fastener it gets a little bit complicated. But just take my word for it that the method with which you move that wrench makes a big difference in the outcome. Something that most mechanics don't know about because as far as I can tell, there's no training anywhere that I can find in how to properly manipulate a torque wrench. So there's a lot of ways that these fasteners can be tightened wrong during cylinder work, particularly when the work is being done with the engine on the airplane as opposed to, say, in an overhaul shop. And if the fasteners are preloaded inadequately, we've already mentioned some bad things that happen. One is that the bearings aren't properly clamped in place. They don't get sufficient crush, and so they can move. These are some pictures. These next couple of pictures are out of a Cirrus SR20 engine that belonged to a client of ours. He had some recent cylinder work at a routine oil change. We found some metal in the oil. We were worried about it. We sent it out for scanning electron microscope evaluation, and the SEM report came back and suggested that the metal that we were finding in the filter was very likely crankcase metal, which suggested to us that there had to be fretting going on. And indeed, we wound up tearing down this engine and finding that that in another 10 hours or so, it probably would have come apart in the air. And that was kind of scary because this was actually a training school airplane. And it probably could have very easily wound up killing a student and an instructor if this thing had come apart. So we caught it in the nick of time. But this is the bearing support in the crankcase, and you can see all of the fretting that indicated that this bearing was not clamped tightly. It was moving around like crazy. Here's what the back of the bearing shell looked like. The bearing shell is steel. The crankcase support is aluminum. So the fretting is more obvious on the crankcase because it's softer material, but you can see very clearly that this thing was moving around. It had moved enough that there was the oil holes were not aligned quite properly, and there was an obvious accelerated wear of the bearing surface due to lubrication failure. And when you looked on the crankshaft, the main journals of the crankshaft, you could also see evidence of scoring, that oil was being cut off to the rod bearings. And had this gone just a little bit further, the result would have been this. Here, this is a Continental engine that threw a rod due to a spun bearing. It's a very catastrophic event. So at any rate, we need to take this stuff very, very seriously. Let me just wrap up by giving you some takeaways from this, and then we'll open it up for some Q&A. Cylinder changes are risky business. I hope I made that point. We never want to change cylinders unless it's absolutely necessary, because this is surgery, and we don't want to perform surgery unless there's a really good reason, because it's inherently risky. And it's particularly important to try to avoid changing more than one cylinder at a time, because changing multiple cylinders at one time greatly increases the risk of something bad happening. But if you must change cylinders, and particularly multiple cylinders, then it's very important to take precautions to mitigate the risk. And the real issue I have is that very few mechanics do these things, or at least do all of these things. So if you're doing this work, or if you have a mechanic doing it, this is kind of a checklist of things to ask them about. First of all, we need to clean and thoroughly inspect all of the threads that are going to be reused on studs and through bolts. In a perfect world, we would restud the case and have all new threads, and that would be the ideal situation. And that's what we do. That's what we should do at major overhaul. But when we're changing cylinders in the field, typically that isn't done. So at the very least, we have to carefully clean and inspect the threads of all of the hold-down studs, and especially the through bolts, to make sure that they're in good condition. We need to slather them with the slipperiest stuff we can. Continental and Lycoming both have different recommendations. My own suggestion is to use something like Aeroshell 15W50 or 50-weight engine oil with something like CamGuard added. That's an anti-scuff agent to minimize the friction. But most mechanics are reluctant to slather all these things with oil because it makes a mess, but it's absolutely critical to do that. Never reuse nuts. Never reuse hold-down nuts. Never reuse through-bolt nuts. Always install new ones. We can't always get the male threads replaced with new ones, although we would in a perfect world. But at the very least, let's not reuse the female threads. Let's replace all of the nuts that we use, and never try to reuse them. It's this is so critical that spending a few bucks on new fasteners is really the only responsible thing to do. Obviously, we want to use a properly calibrated torque wrench and follow the manufacturer's specified torque values and torque sequence to the letter. The torque sequence on cylinder installation is usually a fairly complicated affair. For example, Continental specifies not only a tightening sequence, but specifies that all the fasteners be torqued to about 1/2 their ultimate torque in a particular sequence, and then you go back and torque them again to their final torque. And take great care to achieve the final torque with one smooth motion of the torque wrench rather than taking multiple bites, something that very few mechanics are aware of makes any difference. When removing multiple cylinders, we want to install torque plates and re-tighten the torque, the through bolts. I'll show you pictures of those in a minute. I just finished doing that on my own engine, and I'll show you the way it was done to make sure that there was no chance of bearing displacement. But basically what we want to achieve is, first of all, never to allow more than one pair of through bolts to be torque relieved at any one time. So if you ever see a mechanic that's just taken all the cylinders off an engine, that means all the through bolts have been torque relieved, and there's essentially nothing holding that engine together except for the little bitty bolts along the edges of the case, which really don't do very much. We always need to make sure that all the through bolts are torqued except for one pair at a time, which means that we can remove one pair of cylinders at a time. And we never want to rotate the crankshaft and put any rotational stress on any of the bearings when any of the through bolts are torque relieved. Now, these precautions aren't hard to take, but most mechanics don't bother with them because they don't understand the importance of it. So that's the reason that I am trying to preach this gospel. Let me show you what I'm talking about when I say torque plates. There are various kinds of torque plates, but the ones that we used when we worked on my engine recently, did a top overhaul, were these. These are basically some old Continental cylinders where we just cut off the base flanges and use them as torque plates. A torque plate is just something you install in place of a cylinder so that you can torque the fasteners back up while the cylinder is off the engine. And we were actually, on my engine, we were doing a particularly heavy top overhaul because we not only replaced all 6 cylinders, but we replaced all 6 connecting rods as well. And so here's a picture of that engine with all the cylinders off and all the torque plates on and all of the fasteners torqued up. So even though this engine doesn't have cylinders on it, it is just as firmly clamped together as a fully assembled engine. And so as each cylinder came off, the torque plate went on in its place, and the fasteners, particularly the through bolts, which are the really important ones, were torqued back up to final torque before we go on to the next cylinder. And if you do it that way, and you and careful not to rotate the crankshaft while the through bolts are untorqued, then there's virtually no chance that a bearing is going to be able to get displaced. So this is just a kind of a laundry list of precautions that you can take to make sure that if you are doing cylinder changes, that you'll minimize the risk of something coming apart along the lines of those couple of accidents that we take a look at. So, the final message is be careful out there. And with that, Charlie, well, why don't we just open it up for some Q&A?
Sounds great, Mike. Another informative presentation. I learned quite a bit from this one, so thank you for that. Don wants to know, I have a digital oil pressure display, EDM 930, and I have always seen a fluctuation of 2 to 4 psi at cruise. How much is too much fluctuation?
Well, that's a good question. I don't know that there's a real rule for that. And I also, when you say fluctuation, I don't know how rapidly or slowly that is. I mean, it's normal, for example, for oil pressure to change somewhat as oil temperature changes, and that's particularly true if you're using a single weight oil. So slow fluctuations that would correlate with temperature changes are acceptable. Rapid fluctuations, something that maybe might be termed fluttering oil pressure is always a very bad thing. Now again, I don't know the characteristics of the oil pressure sender in your particular system. I know that when you're looking at a digital readout of oil pressure, if the oil pressure is right on the edge between two possible digital readouts, like for example in the JPI, it may be that it's reading out to the nearest 2 psi or something, and that if it's right on the hairy edge between 50 psi and 52 psi, then it might flutter back and forth between the two, and it would not be meaningful, because what it really is telling you is it's just kind of right on that edge between 50 and 52. But if it's moving much more than that, then I would be inclined to be a little bit worried. I guess that's the best I can do to answer that question.
All right. And Walt would like to know, does a lubricant have any negative effect after the bolt is torqued wet?
No. And you know, again, both Continental and Lycoming are very insistent that the bolts have to be thoroughly lubricated before you put the nuts on and torque them down, for the reasons that we talked about. Because the more friction there is on the threads, the less preload you get on the fastener. And the ultimate goal is not to apply torque. The ultimate goal is to achieve the necessary preload. But we use a torque method to get it, and friction just dramatically affects how much preload we wind up getting. So it is absolutely crucial that the fasteners be very, very well lubricated at the time that they're torqued down.
Okay, Nick is shopping for a debonair, and he asks, what should I do if interested in a plane that has had a recent top overhaul?
Well, good question. I guess first of all, it might be worth finding out who did the top overhaul, and it might be worth talking to the shop or the mechanic that did it, and sort of quiz them on the procedures they used. And again, I don't want to magnify this unnecessarily. A lot of cylinders get changed. You know, tens of thousands of cylinders probably get changed a year, and you know, probably less than half a dozen of those airplanes wind up falling out of the sky. But you know, we're in kind of a zero tolerance business, and we don't want any of them to fall out of the sky. So I'm not, you know, I'm not trying to say don't ever change cylinders, or don't ever buy an airplane that's had a cylinder change. I mean, that would just not be practical. What I am saying is that the whole business of cylinder changes has to be approached as the risky procedure that it is. Just say like open heart surgery. I think of a top overhaul like open heart surgery. It should make you very nervous. That doesn't say you don't ever do it. It says that if you have to do it, first of all, you don't do it unless you have to, and second of all, if you have to, you use every possible precaution to make sure that nothing bad happens. And that's really the message I'm trying to get across. So just to answer your question directly, I would want to know who did the work, and I might want to talk to whoever did the work to find out what techniques were used. And I guess that's the best advice I can offer.
Okay, a couple of questions have come in with kind of the same general question, question, and then that's basically, do you ever go back and retorque the cylinders on some sort of schedule, you know, following the cylinder work?
Some people recommend, and I certainly can't argue with this recommendation, that it's a good idea to go and recheck the torque once, you know, somewhere on the order of 25 hours after the cylinders have been put on. I've never heard anybody recommend doing it on a recurring basis. because if the cylinders are torqued correctly, and if the mating surfaces are clean at the time that the fasteners are torqued, then they're basically on there for life. There's no possibility that they're going to loosen up. The only way that they will loosen up is if either the appropriate preload was not achieved when the things were first installed, or if the surfaces were not clean. I've seen numerous cases where some paint was on the cylinder flange or the cylinder deck that somebody didn't understand, that you can't paint those things. There's a very famous case that I wrote a full-length article about, of a Continental engine that came apart because a mechanic used some sealant that actually came from Continental on the cylinder base O-ring. You're not supposed to. You're supposed to use nothing but engine oil. The presence of the sealant in that joint caused the cylinder to detach itself in flight and resulted in a fatal accident. And there was a very, very large and nasty lawsuit as a result of that. Continental took a bath because their service manual didn't clearly state that sealant could not be used. It now does in all caps and in a big box. But so there is a good argument for rechecking the torque after about 25 hours. I wouldn't do it on a repetitive basis. Rechecking it once is a good idea. The problem, of course, is that after you reassemble all of the baffles and intake and exhaust and stuff, you don't always have access to all of the fasteners. So I think perhaps a reasonable compromise would be to go back after 20-25 hours and put a cylinder base wrench on all of the fasteners you can get access to without major disassembly, and check the torque on those. I think that's probably a reasonable thing to do.
Okay. Barry would like to know, why is changing two opposing cylinders more dangerous than changing only one of them? Don't the same preload issues exist whether it is one or both opposing cylinders?
Yes, and I think that's a fair comment, that if we're talking about changing two cylinders that share a common pair of through bolts, then that probably is not riskier than changing either one of those cylinders. I think that is a fair comment. When I talk about the perils of multiple cylinders, I suppose it would be more accurate for me to talk about the perils of loosening multiple pairs of through bolts, because that's really where the crux of the problem. So I think that's a good comment. Thank you for that.
Okay. And Stephen would like to know, how do you cut the torque plate out of the old cylinder? Bandsaw, question mark. And then another person had asked kind of a similar question, which is, where can you get a hold of what you use for torque plates? I don't know if you I assume you just made those. But does anybody actually sell them? I guess is the question.
Those Continental torque plates that I showed you were homebrew, and they were indeed made by cutting the bases of cylinders off with a bandsaw. Lycoming actually has a part number for an official Lycoming torque plate. I cannot tell you whether or not those parts are available or not, because I haven't tried to order them. But I do know that Lycoming actually has in their illustrated parts catalog torque plates that have an official Lycoming part number, and that at least at one time, if not now, you could purchase from Lycoming. As far as I know, Continental does not, and that torque plates for Continental engines need to be home built. Let me also point out that for shops that don't change a lot of cylinders, there are some alternatives to using torque plates. For example, I've seen conscientious mechanics who cared about this thing. You just use a stack of washers. Whatever you use to simulate that cylinder base so that you can torque those through bolts back up will do the trick. And so there's nothing wrong with using a stack of washers. The torque plates are a little bit better. But the main idea is that before you relieve the torque on a second pair of through bolts, you want to make sure the first set of through bolts are torqued back up. And the only way to do that is to either have a cylinder in there or have something else that has the same thickness as the cylinder base flange in there so that you can torque those things back up.
Okay, and Mike would like to know, do you lubricate the threads and the base of the nut where it contacts the deck?
Yes, you lubricate everything. It should be slathered and dripping with lubricant.
All right, and John would like to know, is the torque specified in the manuals for the wet torque?
It is. That's exactly what's specified in the manuals. Both Continental and Lycoming overhaul manuals explicitly specify that wet torque be used, and they both specify the lubricant to be used, and they're a little bit different. Continental recommends the use of 50-weight engine oil. Lycoming recommends, if memory serves, a 90-10 mix of 50-weight engine oil and STP. I'm not even sure if you can still buy STP. You remember Andy Granatelli? He used to push that stuff, but it's an anti-scuff additive. But basically, oil with an anti-scuff additive is the right thing to use.
Okay, and Stephen chimes in and says, Lycoming insists that the torque plates be used, and the part is available from Lycoming at about $800 each.
Oh my God, I was afraid that he was going to say that.
And then he says the instructor from Lycoming made his own.
In other words, they're as expensive as the cylinder.
Yeah.
The instructor from Lycoming made his own. Very good.
Yeah.
Okay.
Yeah. Another person.
That's a great answer to that question. Yeah. Thank you, guys. I love these Q&A. I always learn from myself.
Barry would like to know, how expensive are the new through bolts?
Gosh. I haven't priced out a through bolt. I just paid for a bunch of them. I should go look at my invoice, I guess. I don't know right offhand.
Okay.
I don't think the cost of the through bolts are exorbitant. The problem is that it is not easy to change a through bolt on an engine that is hanging on an airplane. So generally, it's not done.
Okay. I'm going to summarize a couple of questions here about, well, Gary's is probably as good as any. He says, at 45 hours since, am I past the danger zone of time? There's quite a few questions along that line of thinking about kind of how far away from a cylinder change do you know you're probably okay, or is it done all through oil analysis?
Well, it's a great question. I wish I had an answer to it. And of course, there's no magic answer to it. You can't say, oh, the risk ends at 30 hours. It obviously, the world doesn't work that way. But it is pretty clear that if you get through, say, 100 hours and everything is still holding together, that the majority of the risk has passed. I wish I could quantify that better, and unfortunately I don't. There really isn't any data on that.
Okay. John states, we just reassembled an IO360. We torqued the cylinders as specified, but the studs, bolts were dry. Since we need to retorque them, would you do one cylinder at a time, taking one nut all the way off, lubing it, and then back on and retorquing before moving to the next stud?
Let me think about that for a minute. I guess I probably would. Yeah, I guess that's the best procedure. It's kind of unfortunate that it went together dry. But yeah, I guess that's probably would be the best procedure, would be to relieve one fastener at a time, inspect it, lubricate it, and torque it back down to final torque before going to the next one. I think that would probably be the wisest procedure given that particular situation that you're in.
Okay, and Joseph has a follow-up regarding the answer about checking the torque on the cylinder bolts 20 to 25 hours after reinstallation. What is the proper procedure for a torque check? I have seen some manuals that define it as setting the torque wrench to the minimum allowable torque and applying it to the nut, and other sources that say the nut has to be loosened and then retightened to complete a torque check.
Well, I guess to establish the torque accurately, you would have to loosen the fastener and retighten it. However, it seems to me the risks involved in doing that are greater than is warranted for this, just for the purpose of this check. So I would be inclined simply to recheck the torque statically without loosening the fastener. Basically, what you're trying to do is just is not establish the torque exactly, but to make sure that nobody had a major brain fart when the thing went together. So I would not loosen the fasteners, although to accurately establish the torque, you'd have to do that. But I just don't think the risk in doing that is worth the reward.
Okay, and then Walt would like to know, what are the risks of over-torquing?
Well,
and,
you know,
and could the use of any of these lubricants ever get into that situation?
No, they couldn't. And the risk of over-torquing is, of course, that the fastener would be stretched to the point that it went beyond its elastic phase into the plastic phase where it's permanently deformed. However, you would have to over-torque the fastener by such a large amount in order to overstress the fastener that that the likelihood of that happening is essentially infinitesimal. I mean, as it is, a lot of these fasteners, the specified torque is pretty scary. It's particularly true on continental through bolts. The big bore continental through bolts, like on my engine, the latest torque spec with the 12-point nut is 800 inch-pounds. 800 inch-pounds is a lot of torque. It's scary when you apply it. And in fact, we've actually had some cases where the nuts cracked under the torque because they're right at that's a lot of torque to put on a nut. And in order to get the torque that high, it used to be 600. And then Continental had some engines come apart, and they revised the spec to 800. And to get up to 800, they had to replace the conventional 6-point nuts with 12-point nuts because the 6-point nuts were stripping out when you applied that much torque to them. So this is a system that's under a lot of torque.
Okay.
But I've literally never heard of a case where these fasteners were over torqued to the point that the fasteners deformed. The case is the problems are always with under torque, which causes the fasteners, the joint to fret and then the fasteners to shear. And again, if you remember that slide with the little scale on it, if the preload on the fastener is greater than the maximum load that joint ever sees, then effectively the fastener never feels the strain. But if the strain exceeds the preload, then the fastener feels the strain, and since the strain is happening, 4,800 times a minute or something like that, the fastener, if it feels the strain, will eventually fail in repetitive stress fatigue, which is what happens.
Okay, Joe would like to know, what's the best way to clean the hold down studs? I mean, is it just a wire brush, or?
A solvent and wire brush is the only way I know of. I don't know of anybody that makes like a special thread chaser for these things. they might exist. I'm not aware of them. We always just use a wire brush and solvent.
Okay, and Marty would like to know what should be done about corrosion on the cooling fins on the front side of the cylinders 1 and 2.
Would you say that again, Charlie? There was a little bit of breaking up on that one.
Marty would like to know what should be done about corrosion on cooling fins on the front side of cylinders 1 and 2.
Corrosion. Well, I don't think anything should be done about it. Actually, I mean the only thing you could do about it would be to apply some sort of primer and paint. But I don't think that's a good idea because it interferes with the ability of the cooling fins to shed their heat. The cooling fins are supposed to kind of be rough, and because that kind of maximizes the surface area of the fin that's exposed to the air. That's why they're not polished. And so my recommendation would be not to not mess with them and try to corrosion-proof them, because you would interfere with their functionality in terms of heat dissipation.
Okay, and Gary states not all the nuts are accessible directly with a socket. How do you compensate for the torque loss due to the right angle attachments or wrenches?
You should never use a right angle attachment of any kind. The nuts are always applied with cylinder base wrenches, which are special kind of offset wrenches designed for this purpose that have a big bow that goes around the cylinder fins. But they're designed so that there is no offset in terms of where the torque wrench drive is versus where the socket is. So no adjustments are necessary when using proper cylinder base wrenches. If you're tightening these, at least on Lycomings and Continentals, if you're tightening these things using a crow's foot or something like that, then that's just not an authorized procedure and shouldn't be done.
Okay, and Gary states, last annual I had a number 6 and number 4 removed. Let's see, valve issues, and number 4, a bad exhaust face. My A&P replaced all nuts and studs. He would not let me help at all. I observed all the retorquing, and he did work you would be happy to see.
Great, great. I'm happy.
So there are a few guys out there doing it right.
Yeah, well, you know, it really pleases me when I see something like that. And the problem is that an awful lot of mechanics, you know, I don't want to say aren't that conscientious. I think it's more a lack of education than it is a lack of diligence. It's just that most mechanics haven't been trained in this stuff to realize what the risks are and what needs to be done to avoid the risks. And to be honest with you, a lot of the maintenance documentation from Continental Lycoming isn't all that helpful. I mean, they in my view, they should stress all of this kind of stuff. And from my standpoint, they aren't clear enough as to all the steps that should be taken. I've never seen anything in a Continental manual talks about using torque plates. I have in the Lycoming manuals, but it's sort of obscure and most people ignore it.
Yeah. So Jerry says, from a retired automotive machinist, thank you. Excellent presentation with critical information. So
thanks. I appreciate that.
Appreciate hearing that. What about the difference in accuracy between click style torque wrenches and digital styles?
You know, I have to plead ignorance on that because I've always used click style wrenches because I'm not rich enough to buy the digital ones, and so I don't have any firsthand experience with regard to using the digital ones. I mean, I assume the digital ones are more accurate, and if I did enough of this stuff, I'd probably go spend the money on a digital snap-on torque wrench, but I don't, and so it's not within my my area of personal experience.
Excellent. And then,
at least I use snap-on torque wrenches and not the kind from Harbor Freight. Nothing against Korean torque wrenches. Now you understand.
Rob states, if moly grease is the slipperiest, is it the best to use it for the torquing?
Neither Lycoming or Continental talk about using grease. As I said, Continental talks about using 50-weight engine oil, and they don't specify what kind of engine oil. There's a big difference between Aeroshell W100 and Aeroshell W100 Plus. And in my view, W100 Plus would be a much better lubricant for this purpose, but they don't talk about that in the Continental manual. I just say 50-weight engine oil, leave it the rest of your imagination. Lycoming says a 90-10 mixture, if memory serves, they say a 90-10 mixture of 50-weight engine oil and STP. And I'm not even sure whether you can still buy STP. But again, if it were me, I would use aircraft engine oil that has an anti-scuff additive in it, whether it's Aeroshell W100 Plus, whether it's straight weight oil with the Lycoming LW16702, I think it is, snake oil anti-scuff additive in it, or whether it's engine oil with some cam guard added. That's what I would use for this purpose is engine oil with some anti-scuff added to it.
Okay, and Dennis has 2,500 hours on an 0360 Lycoming. Our oil consumption is, not surprisingly, rising. 3 hours per quart, and the oil is getting dark within 5 to 10 hours of an oil change. We are considering a top overhaul. Since we have no metals showing up in our oil analysis, do you have any issues with that maintenance logic, assuming our mechanic follows your guidance?
I have no issues with it, and in fact, that's exactly what I just did to the left engine on my airplane, whose oil consumption was going through the roof. Primarily because after 3,200 hours, all of the oil control rings were kind of stuck with lead and stuff, and the cylinders hadn't had crosshatch on them for about 15 years, and I mean, these things were just worn too. To say that they were fully depreciated would be understating the case. So, but because there was no evidence that there were any bottom end problems with the engine, at 3,200 hours since major overhaul, I opted to top the engine. I don't think there's anybody else in the entire universe that would do that besides me. Most people would laugh at that, but it seems like the prudent course of action, and that's exactly what I've done.
A couple of people have chimed in. STP is available on Amazon, and and also a couple of questions.
Andy Granatelli lives.
Yeah, a couple of questions around where do you go to get your torque wrench calibrated?
Oh, there are tons of services that do torque wrench calibration, and also you can buy torque wrench calibrators now for not a totally unreasonable amount of money. And it's only worth doing if you have a lot of torque wrenches, if you run a pretty big shop. But you can get your own digital torque wrench calibrator, or you can send them out. There's any number of people that do it. In fact, I think, I'm pretty sure if you have a Snap-on torque wrench, you can hand it to your local Snap-on truck driver, and he'll take it away, get it calibrated, and bring it back to you. I sent mine out to Snap-on's repair depot, and they turned it around about a week and sent it back to me all calibrated.
Okay, and Dennis would like to know, would you lube prop extension bolts into the crank flange?
I don't know. I would have to look in the manual to see whether they specify wet or dry torque. My guess is they specify wet, but I don't know. I'd have to look at the book. I mean, if you're torquing something to a specific torque spec, you need to use the procedure that whoever it is came up with that torque spec wants you to use.
Okay, and Tom Tom just shares that I calibrate torque wrenches at my EA chapter once or twice a year. Unfortunately, I'm not a member of Tom's chapter. Otherwise, you'd be saving a few bucks.
Well, maybe you need to come up with an inter-chapter arrangement for that.
Another great idea. Well, Mike, we're
how about a torque wrench recalibration booth at AirVenture where everybody brings their torque wrenches in once a year?
You know, that might not be a bad idea. Group discount.
There you go.
Well, Mike, I want to.
Somebody could pay for one of those digital torque wrench calibrators real quick that way.
That's right. I want to thank you for the excellent presentation and taking the time answering the questions. Is there anything else you want to add?
Well, yeah, just very briefly, I just wanted to talk about the next couple of first Wednesday of the month webinars we're going to be doing. As you mentioned, Charlie, the one in September, on September 2nd, it's going to be all about alterations. We're going to be talking about major alterations versus minor alterations and how you can tell which is which, and whether you need a field approval or not, and all that kind of stuff. There's a tremendous amount of confusion about that. So that's what the September webinar is going to be about. October is going to be about oleo pneumatic shock struts, which are and how they work inside and how they're maintained, and how you know whether you need nitrogen or whether you need more fluid and that sort of thing. And then finally, in November, leading up to the winter season, we're going to be talking about carbon monoxide, which is particularly a risk during winter flying when people use their cabin heaters. So those are the next three webinars coming up. And let me also just mention that anybody who isn't already doing so can sign up for my free monthly e-newsletter, either by going to my savvyaviator.com website and putting in your email address, or during the post-webinar survey that Charlie's about to unleash on you. There's a checkbox that you can check, and you can get on the newsletter list. Every newsletter has an unsubscribe link, so if you have reader's remorse, it's very easy to get back off the list. And finally, if you haven't looked at it already, check out my book manifesto that talks about my maintenance philosophy and stuff. It's available on Amazon for some ridiculously low price, $12 or something like that. And that's about it, Charlie.
Well, great, Mike. And if you want to support EAA, we also sell the book, as I recall.
Indeed.
And
selling it at AirVenture. I didn't hear whether you guys sold out or not, but hopefully.
And I will just mention that since you didn't, your excellent website, Savvy Analysis. So if you are pulling your engine data, it's a great way to look at your temperatures and all your engine parameters that you get out of your wonderful digital engine analyzers these days.
Thank you for that.
I've used it many times.
Very good.
And it is excellent. So with that, I appreciate everybody for being an EAA member and tuning in tonight. And Mike, we will be with you again next month.
Excellent.
Have fun, everybody. Be safe out there.
Good night, everybody.